Hello, class. This is problem number 2 on the group work assignment, which says calculate the magnetic field strength with a distance of 1.5 centimeters from the axis of a 2 centimeter radius capacitor with 1 millimeter spacing that is being charged by 1.5 amp current. So our given values, you can see off to the left, and we've got two different values of a radius. Because as we're setting it up, we have the distance, and we put that as little r as the 1.5 centimeters. And we've also got the radius of the capacitor itself, which we need, to calculate an area eventually. And that's 2 centimeters. And then we have a current. And then we're also given a spacing, a distance within the capacitor. So those are those four values. And we need to find B, the magnetic field strength.
Right. So we'll start off here with our lovely equation, Maxwell's equation for an Amperian loop with his correction thing here. So our line integral of B dot ds is going to be equal to mu naught times the current contained, which in our case, we're actually looking at a point that's between the plates of the capacitors. So there's not any current carried in a wire contained there. So that goes to 0. And then our second term, his correction factor, I believe, which is mu naught times epsilon naught times d phi dt, so the change in flux. So we'll come over here. Our flux for our electric field in there is going to be E times A, and I call it A sub G because that's the area of our Gaussian surface, or our imaginary surface that's circumscribed by that 1.5 centimeter radius. And then our E field is going to actually be equal to the charge divided by the area of the capacitor times epsilon naught. And so we take this and plug it into here and plug this whole thing into here. And let's see. So we have our line integral just becomes B times 2 pi r, which is the circumference. That's our ds here is. So we got our magnetic field times the circumference of our imaginary surface, or imaginary circle there. And that's going to be equal to mu naught times epsilon naught. And we actually can pull the d dt out, or separate it from that phi, and plug this in for phi. So we've got that q over a epsilon naught times the area of our Gaussian surface. And then further reduction gets us this. The d dt combines with the q and becomes dq dt. So the rate of change of the charge, which is our current, will turn into I, and then some cancellation here. And this is, again, this is our area of our surface, pi times little r squared, and then our area of the capacitor, pi times big R squared. And it reduces to this. So we divide 2 pi r over and do some further cancellation, and we get that B equals this expression right here, mu naught IR over 2 pi big R squared. And plug in our numbers, and we get that our magnetic field at that radius is 0.01125 milliteslas.
And you can see that the units work out.
Yep, indeed. All right, thanks. Oh, and one last thing, if you have any questions, refer to the video on Maxwell's equations, and that should help you. Cool.